Now, for the next set of problems we're going to start working out on is called the inverse square law. The inverse square law tells us about the intensity of the X-ray beam when the distance varies. The closer the X-ray beam is to the source, the more intense it is, and then the further away it is, the distance, the intensity gets less. That's why it's inversely squared. You see here I have the formula up. It's I1 over I2. I1 is the original intensity, and I2 is the new intensity. Then on the other side, which is the distance, so I1 over I2 equal to SID2, or the distance 2, over the distance 1, which is the original distance. Now, you have to be very careful when it comes with the inverse square law, especially for the distance. The first distance is at the bottom, and then the second distance is going to always be at the top, or the new distance. We do things by a source to image distance. That's what SID stands for. Our very common SID that we use in X-ray are two of them. One is 40 inches, the other is 72 inches. So again, at 40 inches, the X-ray intensity is going to be more intense than when we pull away up and increase our distance to 72. I'm going to work out a few problems to better demonstrate this inverse square law. I'm going to work out an inverse square law problem. There's the formula over the left. I1 over I2, SD2 squared over SD1 squared. My first intensity is 200 millirentgen. The second intensity we don't know. We're going to solve for it. But we do know our distance. Our first or original distance was at 20 inches. And then we increased our distance to 50 inches. So I'm just going to go ahead and start off by plugging everything in the problem. So as I start off, I'm going to plug everything exactly into the formula the way I have it. It's going to be 200 over the X, because I don't know what the second intensity is. Then I need to find my second distance, which is 50 inches, and I have to square it. And then my original distance is at the bottom, which is 20 inches, and I have to square it. Now this looks like it's ready for me to solve. I need to isolate X. But before I do anything, what I like to do is first simply simplify what I can. And I can simplify the, remember the reduce the fractions? I can simplify the 50 over 20 before I actually square them, to make it simple for me to work out. What they have in common are the multiples of 10. Right? Which 50 into 10 is like 5. 10 into 20 is like 2. I'm still going to square them both. And I'm going to just bring everything else down. They stay the same. Next, I'm going to square these two, which 5 times 5, or 5 squared, is 25, and 2 squared is equal to 4. Now, this problem looks like a ratio problem, and that ratio is simply cross multiplying. 25x equals, and then 2 times the 4 equals We got to get x by itself still, so 25, and I have to do the same thing on the other side, 25. Our unknown intensity 2, is simply going to, well, 800 divided by 25, okay? It's simply going to be, for us, for this next lesson, we're going to learn about the density maintenance law, or how to maintain the density. We do need to maintain the density when we increase or decrease our SID, our source to image distance. As we know from the inverse square law, that when we're close to the image receptor, the intensity is very great, but yet when we get further away from the X-ray source, the intensity is less. And sometimes we need to maintain our technical factors to compensate for when we do increase or decrease our distance. And again, the technical factor that we use is mass. And I have the formula right before you. You'll see it's similar to the inverse square law, but it's actually totally different. What makes this different is to maintain the density, it is actually a directly proportional problem. It is not an inverse proportional problem like the inverse square law. So at the original mass, which is mass 1, is over mass 2, which is the new mass, which is equal to the first distance, or SID, squared, and then over the second distance of SID squared as well. So the first mass is going to have probably a certain technical factor at a certain distance. And then when we increase the distance, well, sometimes we have to figure out what is going to be the new technical factor. So let me go ahead and start by working some examples on how to maintain density when we increase or decrease our distance. Now, here's the problem I'm going to work out with you with maintaining the density. First, the first mass was at 10. We don't know what the second mass is going to be, but the mass at 10 was at a 20-inch SID, and now we've increased our SID to 50 inches. Again, we have increased the SID to 50 inches, from 20 to 50. So I'm just going to plug everything into the problem. The first mass over the unknown mass. Now the first distance over the second distance. And they both have to be squared. So now we can go ahead and kind of work things out. But what's best for us to do is, again, reduce, similar like we did the inverse square law. And what I see here that they have in common, the greatest common multiple would be 10. They are both divisible by 10. I'm going to do that before I square things. So 20, 10 gives me 2, and 50 to 10 gives me 5. I still have to square everything before I move on. So when I square, 2 times 2 is 4, 5 times 5 is 25. I'm just continuing to bring things down. 10 equals x. 10 over x equals 402. This is where I get to cross multiply. 4x equals 10 times 25, which is 250. Of course, divided by 4 to get x by itself. Now x is equal, well, this is going to figure out our new max. And it's 62.5. 62.5. Even though we started off with a mass of 10, and because we increase our distance, we must increase our technique to compensate and maintain that same density to 62.5 when we increase our inches to 50. Okay? So at 20 inches, our mass at 10 was good. So we want to maintain that same good x-ray when we increase our distance to 50, and so we have to increase our mass to 62.5. Let's work out another one. So this is our problem we're going to work out. A satisfactory radiograph is made at 8 mass at a 72-inch SID. How much mass is needed to produce a similar radiograph at 40-inch SID? So we're going to start by kind of plugging in some numbers. Well, we know what the first mass is. It is 8. And then we know what the first SID is, which is 72. First mass, 8. First SID, 72 inches. And then we're going to figure out what happens when we change our SID to 40 inches. But we need to figure out what is our new mass. Here's the numbers that I'm getting. The first mass is 8. The second mass, we don't know. Our first distance is 72. Then we decrease it down to 40. Don't forget to square those distance. Next, I like to reduce the fraction. I know both of them can, the greatest common multiple between the two is 8. So this goes to be 9 squared over 5 squared. 8x equals 81 over 25. 81x equals then, because I'm cross multiplying, is 400. Get x by itself, I'm dividing 81. X is equal to 4.93827. And the numbers keep going. But I'm going to round up, or excuse me, I want to round, and I'm going to use this number to round. So since this number is 3 and below, or 4 below I should say, it's going to be 4.9. My new technique, since we decrease, is going to actually be 4.9 mass. So at a greater distance, our mass or our technique is at 8. Now at a lesser distance, our mass is nearly halved at 4.9. If you have any more questions in regards to how to maintain density, please look into your text in Chapter 3 under right after the inverse square law. And also, please make sure you do the practice problems to help you retain the information.